Hi everyone, I'm Manqi from Nanjing University of Science and Technology. Today I'm going to introduce our paper IMGDroid, Detecting Image Loading Defects in Android Applications. I will introduce the following aspects of the paper. Android applications often use images not only to enhance user experience but also to better provide their functionalities and services to users. Android SDK provides several classes to help programs to load and display images in apps. Besides, there are also third-party libraries for this, for example, Universal Image Loader, Fresco, Glide, and Picasso. No matter which image libraries is used, the workflow of image loading in Android apps is almost the same. When receiving a request to show an image, the app first tries to read the bitmap object from the memory or disk cache. If there is no cache, it has to load the image externally from the network or the local storage. After some processing and the transformation, the transformed image is then decoded and finally rendered. Developers can choose whether to use a cache mechanism according to their needs. According to Android developers and the reported issues of real-world apps in GitHub, we found that inefficient or improper image loading and displaying operations may severely impact the app performance and quality. Additionally, I think these image loading defects may not be manifested by immediate failures, for example, app crashes. Existing geotexting approaches can't detect them effectively. Thus, in this paper, we aim at detecting image loading defects in Android apps. Based on Android developers and the reported issues of real-world app in GitHub, we summary 5 patterns of image loading and develop an automated static analysis to detect image loading defects based on these patterns. This is the 5 patterns of image loading. They are respectively image passing by intent, image decoding without resizing, local image loading without permission, repeated decoding without caching, and finally, image decoding in your thread. This is a specific introduction to the 5 patterns. Due to time constraints, I won't go into details. This is an overview of IMGDroid. The input is an app and the output is image loading defects. IMGDroid is based on Suite and FlowDroid. To scale to large commercial apps, IMGDroid detects image loading defects by combining a context-insensitive caller analysis and a path-sensitive inter-procedural control flow analysis. Starting from the image loading statements, IMGDroid utilizes different static analysis techniques, for example, reachability analysis, post-dominator and dominator analysis, taint analysis, and dependence analysis to analyze whether the image loading defects of different kinds exist or not. Since some patterns can occur to different image frameworks, including the Android SDK, our static analysis varies accordingly and is tailored to different image frameworks. Now I will give 2 examples to show how IMGDroid detects image loading defects. This figure exhibits the detect of image decoding without resizing. It uses Android native APIs decode stream to load the image at line 8. For Android native APIs, if the decoding statement doesn't have the argument, for example, options for image resizing, the image is decoded but not resized. Otherwise, we further check whether the statement that reduces the image size, dominates the decoding statement. In this figure, the decoding statement at line 8 have the argument options for managing image, but its argument options is not adapted between line 5 and line 8 as suggested in Angel developers for image resizing, so that the image is decoded without being resized. This figure exhibits detective imagery detecting repeated decoding without caching. The method decode file of image loading is implemented in the component's callback function's gather view. Our analysis method is based on the inter-procedure control flow graph of the app. We checked image decoding statement where the decode file method is located is not post-dominated by a corresponding image coding statement. Each time the callback get view is triggered, the statement at line 3 will decode the image repeatedly. Due to the limitation of time, I have to skip other methods, but their specific introduction. In this section, to evaluate the effectiveness and the efficiency of IMGDroid, we first evaluate our approach by an experiment on 21 open source apps with 45 known image loading defects. To extensively investigate the prevalence of image loading defects in practice, we conduct a large-scale empirical study on 1,000 commercial apps randomly selected from Google Play. This is the experimental setup, and the IMGDroid is open source. This is the URL of IMGDroid. In the experiment of a benchmarker of 21 open source Android applications, we found that it not only successfully detects the 45 previous known image loading defects, but also finds 15 new such defects. According to the result of 21 Android apps, the static analysis of IMGDroid for detect image loading defects is efficient and tends to perform well in terms of both soundness and completeness. According to the result, there are totally 5,471 image loading defects found in the 865 of the 1,000 Android apps. Only 32 apps that involve image loading operations don't have such defects. For the 865 apps, each app has on average 6.32 image loading defects. The empirical results demonstrate image loading defects are common and severe in real-world commercial apps. Such defects have not gained extensive attention from the app developers. In this talk, we discuss image loading defects that may severely impact the app performance and the quality, and we present the file independence. Then we present IMGDroid, a static analysis approach, and an open source tool to effectively detect based on these independence. Finally, we discuss the results of two experiments. The results indicate that IMGDroid for detect image loading defects is inefficient, and image loading defects are common and severe in real-world commercial apps. Thank you for your attention. That's all.
Hi everybody again. So thank you for being here, and we proceed with the second paper. Wei Song is ready to answer our questions. Thank you very much, Wei. So let's start with the first question that it is in the chat. You can see the first one is: you identify 5 anti-patterns of image loading defects, including image passing by intent, image decoding without resizing, local image loading without permission, repeated decoding without catching, and image decoding in UI threads. Okay, this is good to remember because these are the basic components of your work. So is this characterization complete? This is the question. Or are there any additional anti-patterns that maybe you have in mind for future consideration? I felt really curious about that.
Okay. First, we do not claim that the 5 anti-patterns are complete. Maybe there are other anti-patterns. However, from our empirical study, we do not find the other so severe problems. So in this stage, we only consider these 5. Okay, these 5.
Okay.
We do not consider more. Okay, thank you.
Have you in mind any 6th candidate? One anti-pattern that maybe you are hesitating that should probably be considered to extend your catalog, or is not the case yet?
Maybe there are. It's hard to say. I do not find them. Okay. Maybe any other such defects are not so severe, and maybe it is not considered as severe as these 5 anti-patterns. Okay.
Okay, I think that is a good point of your work that, well, it's a conceptual background. You have 5, you have made this a very, very interesting contribution. So it's a very clear starting point. And it's good that you are open to see if other anti-patterns should be of interest for extending the research. So thank you for that. It's clear. Another question is that one, what if we look at other non-Android technologies? Are your ideas generalizable? Any comparative studies with others? It's an important question to me because I find your work very relevant, but it is applied to Android technology. So could it be applied to non-Android technologies to let people benefit from this interesting solution that you are proposing?
Yeah, we believe that our technology, our methods can be generalized to other non-Android technologies. For example, iOS apps. We believe there must be similar image loading defects in such kind of mobile apps.
Mm-hmm. Okay. Thank you. Let me move to another question that is that one. It is there are I see that there are 21 open source Android apps in your experiment. So do you consider that they are enough? Are these 21 open source Android applications enough for the experiment? And also related to that, how did you choose them in order to try to cover as much diversity as possible?
Okay. In fact, I think 21 open source Android apps are not so sufficient, but we can only select these because we at the time we studied this problem, we can only find such issue reports in GitHub or GitLab. So we can only select these 21 apps as the ground truth because for other apps we do not got the issue report, so we cannot use them as the ground truth for our evaluation. So this is the reason why we only choose 21 open source apps. We choose them just from the issue report of the GitHub or GitLab. Okay, and the developers' feedback for these defects. Okay, this how we choose them. Okay.
Okay, thank you. Yes, it's clear to me. The next question is somewhat related to this one. It's just going further. It is the next one. It is how did you identify the selected image loading defects from GitHub or GitLab? Were these sources or defects reliable and representative? The representation is important in the sense that it is relevant to know if you feel that the diversity of problems is properly, adequately managed with this selection that you have done. And this is the last part of the question. Can genericity be assessed, or on the contrary, could it be the case that the problems that you are selecting were specific, or they were too related to a very particular case or a very particular technology?
Okay. So I think the problems or the defects are generalizable because for several anti-patterns, other research papers also investigated similar problems. Okay, I think they are generalizable, and besides, we also conduct a comparison performance comparison study. We fix these defects, and then run the apps before and after fixing, and we found that the performance are different. And after we fixing these defects, the app performance will get better, become better. So this confirms that such kind of anti-patterns really undermines the performance of app.
Okay, Wei, thank you. I thank you very much for your clear answers. I have a last question for you. That is the one related to the last part of the experimentation case. You're jumping to the 1000 case. My question is, how did you make this jump to the 1000 application experimentation case? Any particular selection criteria? And I was also curious about the question of if it could be the case that the production strategy were the same in this set of applications. What could explain, for instance, why a given image loading defect is more or less frequent? Because it could be just associated to a particular development method or programming strategy. So this is the last question. This jump to the 1000 case.
Okay. In order to evaluate the defects in practice, we just randomly select 1000 apps from the Google Play, and we do not how to say, we do not pick them by selection. We only just randomly, and we consider both the popularity and their different functionalities, and all kinds of criteria to select them. And we think that these 1000 apps represent the practice and represent the general situation, I think.
Okay, so, well, thank you very much. We are just in time. We have only 20 seconds to go. Thank you very much,
You're
Wei,
welcome.
for your paper.
Okay.
I think that your paper is plenty of opportunities, and it has a brilliant future. I remember all the authors that you can continue the discussion in the discussion room. Thank you very much, and I see you in the next paper. Bye-bye.
Okay, thank you. Bye-bye.